Okay, in this class, we'll cover the contents about the determination of dimensions of polymer chains. So polymers are basically very long chain molecules, right? Very large molecules. Okay. So we want to know what kind of shape, what kind of physical one, relatively macro scale shapes does polymer molecule have? Okay. So in general, we can say that polymer chains are like randomly oriented. Okay. So generally, in many cases, polymer chains exhibit random chain conformation. Okay, so basically they show random distribution of relatively low energy conformation such as trans and Gaussian states. Okay, so I said in many cases, so not all cases, polymers usually this random chain conformation is shown for polymer solution or polymer melts or amorphous polymers. Okay, so in these cases, polymer solution, polymer melts, or amorphous polymers, polymer chains, these long chains show basically this like random polymer chain conformation, which is called Gaussian chain. Okay, so we need to first learn about the conformation of polymer chains or hydrocarbons. We learned about configuration and conformation, right? Remember? So let's learn more details about the conformation. Okay, so this first the case of normal butane. So CH3, CH2, CH2, CH3, 1, 2, 3, 4, right? So the carbon-carbon single bond, the length of this single bond is 1.54 angstrom. Okay, and in 3 dimension, these basically have a certain angle, which is 9.5 degree, right? Remember? Okay, so this is 1, 2, 3, 4, right? As you all know from the organic chemistry class that this single bond, carbon-carbon single bond can rotate, so they can be rotated in this manner, right? So there could be the rotation angle pi, the rotation angle. Okay, so if you look at this, the rotation of basically the change of the position of carbons in this side from here, this is the I. Okay, from here we can determine the Newman projection. Remember Newman projection from organic chemistry class, right? So it could have different conformation such as trans, right? So methyl groups are located in opposite position, so this is trans when rotation angle is 0, okay, or when rotation angle is 180 degrees or pi, the same methyl will be located in the same position, which is this, right? Similarly, when rotation angle is either 120 degrees or minus 120 degrees, basically has this structure, right? Or this, right? So these two are called gauge structure, right? Gauge state, right? So if you draw the energy, potential energy, so energy as a function of rotation angle, 0, 60, 20, 80, minus 60, we'll have like this kind of diagram, right? 60, 0, looks like this, right? Okay, so trans or gauge conformations, especially trans, is the lowest energy state. Also, gauge is a relatively low energy state. Okay, so in nature, polymer chains will have, if they consist of this kind of carbon-carbon single bond, okay, they will exhibit either trans or gauge conformation for each carbon-carbon single bond. Okay, right? All right. So with this in mind, we want to determine the mean square end to end distance. So basically what we want to determine is the overall size of the polymer chains. Okay, how can you determine it? The first method is called contour length. It's basically the total length of the polymer chain. Overall total length. So if we assume that the polymers are linearly located, something like this, okay, so which is called for freely jointed chain. So in this case, the angle, the bond angle, theta, and the rotation angle, both of them are free. So we can just assume that we just simply hold the opposite side and just stretch it, right? Then the overall length of the polymer chain would be simply the length of each bond, right? So basically the bond length, this length, times number of bonds, right? This is the number of bonds, number of chemical bonds. Okay? So for example, bond length is like 1.54 angstrom. Okay? For freely jointed chain, we can say that, but in reality, polymer chains are not freely jointed. Second case is for fixed bond angle, theta, which means that chemical bonds are something like this. I'm sorry. Looks like very weird. Something like this. For a fixed bond angle, theta, 100.959 degrees C. Okay, then the overall length of the polymer chain, if you use the sine value, would be L sine theta over 2. Right? So by simply assuming that polymer chains are linear and either for freely jointed or for fixed bond angle, we can easily determine the overall length, the size of the polymer chains. Okay, but this is not really the real case, right? In real case, polymer chains, as we have already learned, that polymer chains show like random chain or Gaussian chains, right? So we can really say that the end-to-end distance as determined here or here is the real size of polymers. Okay, so in that case, we denote polymer size based on mean square end-to-end distance, or we just say that R square, average R square. So this bracket means average value. Okay. The reason why is that in real system, real polymer chain, the R, the end-to-end distance of polymer chains changes, okay, continuously with time, right? Polymers are moving basically, right? So we need to take the time averaged value. Okay. Also, polymer chains have distribution of the length, right? Many chains with different length. Okay, so we need to take the average. Okay, so polymers have basically random chain motion. So if you want to denote end-to-end distance, how can you determine it? Okay, polymers will have this shape or this shape or some other shape because they change the shape as a function of time. Okay, the simple way is that we just denote each chemical bond, each carbon-carbon bond as a vector. Okay, vector, another vector, something like that. Then we can denote the end-to-end from the start to the end-to-end distance by simply taking the sum of all of these single vector, right? You know what vectors are, right? Okay. By simply taking the sum of all the vectors, we can determine the end-to-end distance R. Okay, so let's do it. So first case is freely jointed chain, as we freely jointed. Okay, so the over end-to-end distance will be sum of all the vectors. Okay, so you can say vector. Okay, and the size of the vector, the end-to-end distance or the R square, can be determined by taking the multiplication of Li and this is J Lj. Okay, if you do the calculation, you get Li square to Li Lj. Okay, this is the overall size of the end-to-end distance. And if you take the average, okay, average would be 1/n times k to n Lk square, which is n Li square plus 2 times n minus 1 Li Lj which is equal to NL square plus 2L square 1 n minus 1 sigma I plus 1 n. Actually, this the inner product of two vector is cosine theta, right? Okay, and we know that the cosine function looks like this. Okay, so if you take the average, it basically becomes 0, right? So for freely jointed chains, the average end-to-end distance R square bracket is simply NL square. Okay, simple. So details will be covered in class, okay? So detailed derivation. Let's see the result. Second case is free rotation. Rotation with fixed bond angle theta. Just see the result. R square average is NL square 1 minus cosine theta over 1 plus cosine theta, right? If you also fix the rotation angle, so fixed theta and fixed phi, the average end-to-end distance is NL square 1 minus cosine theta over 1 plus cosine theta 1 plus cosine phi over 1 minus cosine phi. Okay, so as a result, the average end-to-end distance can be represented as NL square, some function of theta and some function of pi. Okay, and this part is called characteristic ratio. So it depends on the overall conformation of polymer chains. Okay, this is the one way to define the size of the polymer or the end-to-end distance of the polymer chains. Another way is there is another way. It's based on radius of gyration. In this case, if polymer chains look like this, we just assume the polymers are overall the shape of sphere. Okay, and we just take the center of mass and we just measure the radius of this sphere. Okay, that can be done easily by using some specific experimental technique. Okay, so that radius of gyration, the radius is denoted as actually S. Okay, the average of S is equal to R square over 6. Okay, this is another way to define the overall size of the polymer chains, random Gaussian chains. Okay. All right. Okay. Today we'll learn about the overall structure over polymers. So if you look at for example, glass, the window. Okay, window is transparent, right? And also is quite brittle, right? So that kind of material, let's say, is called glass, right? We all know what glass is, right? And if you look at the microscopic structure, molecular arrangement of structure of this glass, their structures are amorphous. There's no specific ordered structures. Okay? Basically like random orientation of like polymer chains. Something like that. Okay? On the other hand, some polymers at relatively low temperature, they show crystalline microscopic structure. Okay? Usually crystalline materials are not transparent. they reflect light. If you imagine the germs, right, diamond or something like that, they are very shiny, right? They basically reflect light, and their mechanical strength is really strong, right? So those kind of materials are called crystalline. So there are basically two different types of polymer structures, amorphous or crystalline. Okay, so amorphous structures basically look like this. No, there is basically no ordered molecular arrangement. On the other hand, crystalline materials have very ordered molecular arrangement, basically the polymer chain arrangement. Okay. First, we need to know what crystal is. Okay, crystal. Okay, crystal. If you recall from, for example, general chemistry class, crystal is basically based on unit cell, right? Basically, there is a unit structure, right? Remember this kind of structure, right? Okay, with different length and different angle. Okay, so basically, unit cell forms the arrangement of unit cell, something like this. Okay, which is called lattice. Okay, and if you form larger lattice arrangement, that results in crystal. Okay, and there are basically 7 different crystal systems, right? Remember? Yeah. Triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, rhombohedral, and cubic. Basically, there are 7 different unit cell structure. Okay, based on that, they can form lattice, and as a result, they form crystal. Okay. So some polymer chains form this kind of very ordered structures. So if you recall tacticity, remember, for example, for a polyvinyl, something vinyl form of polymers, there are 3 different types of tacticity, right? Isotactic, syndiotactic, and atactic, right? Remember? Okay. So isotactic and syndiotactic arrangement of polymer chains, basically the side chain, shows relatively regular molecular arrangement. On the other hand, atactic shows relatively irregular molecular arrangement. Okay? So, if a certain polymer chains, there are polymer chains, something like this, try to form crystalline structures, they should be located in some crystal unit cell, something like this. Let's say the polymer chains are in blue. They should be located in, for example, like in this manner, right? They should be packed in a certain crystal structures. To do that, in terms of tacticity, polymer chain should be more or less regular structure, right? So isotactic or syndiotactic polymers can be considered as crystalline. Not all of them, but they are usually can usually form crystalline structure. On the other hand, atactic or irregular arrangement are amorphous structures. Okay. Okay. All right. one thing to note is that polymers are basically consist of long chains. Okay? So they cannot really form perfectly packed or perfectly crystalline structure. Even crystalline polymers, even if they form relatively crystalline molecular arrangement, they have both crystalline region and some portion of amorphous region. Okay. The reason why is that there are some defect in crystal structure. It could be also there's some side chains or some chain end of the polymer chains which basically disrupt the overall crystalline structure. Okay. So not all polymers, polymers cannot be, in other words, if you say in other words, polymers cannot be 100% crystalline. Okay, so let's go back to the previous section, that polymers basically can be either amorphous or crystalline, but even crystalline polymers are not 100% crystalline, so we say semi-crystalline. Okay, all right. So in this crystallinity can be controlled by treating polymer materials in different way. Okay, so polymers basically have different degree of crystallinity, and there are many different ways to determine the degree of crystallinity of polymer materials. Okay. All right, let's move on. So we have seen two different types of polymeric structure, amorphous and crystalline, semi-crystalline. Let's first consider semi-crystalline polymers. Okay. So I mentioned that even crystalline polymers have both crystalline and amorphous region. So some portions of the polymer chains are amorphous. Then we can have questions. How is semi-crystalline polymer packed? Okay. How does semi-crystalline polymer exhibit this kind of like ordered molecular arrangement? So the first model to explain this packing of semi-crystalline polymers is called extended chain model. In this model, we basically assume that polymer chains are forming this kind of arrangement. So each of this blue line is polymer chain. Okay. In this model, the dimension of polymer or dimension of the crystal formed by this extended chain model, the crystal size or length should be same as molecular length or molecular size, right? Here, molecule denotes polymer. Okay? But in reality, it's not true. Okay? And another problem of this extended chain model is that it cannot explain the existence of amorphous region. Okay? By simply looking at this model, we cannot really explain the existence of amorphous region. Okay? So there is another model come up, which is called fringed micelle model. Okay? in this model, polymers are basically located in this manner. And some chain end something like this. Okay, so by using fringed Miser model, we can explain the existence of crystalline region and amorphous region. So let me use the different color. Okay, this is the amorphous region. Okay, so you can explain both the existence of crystalline and amorphous region. Okay, and some, like a few polymers, show this kind of fringed Miser structures. But the thing is, if you look at the figure in page 409 in the textbook, they show the real experimental data of the polymer crystal. And if you look at the figure, they show basically this kind of plate-like structures in real polymer samples. Okay? So, in this figure, the size of this plate is under some micron, and the thickness is under the nanometer, a few nanometer or tens of nanometer. And using this fringed Miser model, this cannot explain the existence of this kind of structure. Okay, this kind of structure is called lamella. Okay, so we need another model which can explain the existence of this lamella structure, which is called folded chain model. So folded chain model basically assume that polymer chains are forming these kind of lamella plate-like structures in this manner. Polymer chains are forming crystalline structure in this way. So in this kind of structure is like inside of here, right? Something like this. Okay? Okay? So using folded chain model, you can explain the existence of these lamella structures. But the problem also is that you cannot explain the existence of amorphous region, right? So people come up with another model, which is extended folded chain model, which is basically the collection of this kind of lamella structure. Okay, so basically this lamella structure form crystalline region, and some amorphous chains are in between this lamella plate. Okay, it's basically stacked lamella structure. Okay. Right. Okay. So there is a few different types of model which can explain the structure of semi-crystalline polymers. Okay. Now let's move on to how to determine the degree of crystallinity. So even semi-crystalline polymers exhibit both crystalline and amorphous region. Okay, so some portion of the polymers are crystalline, some portion of them are amorphous. Okay, so we need to determine the degree of crystallinity, because the crystallinity also affects the overall properties, physical properties of polymer samples. Okay. So the degree of crystallinity is defined as the ratio. So it could be volume ratio or weight ratio of ratio of crystalline region over total region. Okay, so it should be smaller than 1.0, right, or 100%. Okay, degree of crystallinity. Okay, I already mentioned that real polymers cannot be 100% crystalline. Okay, there should be some portion of amorphous region. Okay, so we learn how to determination of degree of crystallinity. Okay. Okay. So first method is based on density. Okay. So let's say that the density of the crystalline region is rho C, rho sub C. Density of amorphous region is rho sub A, and density of the real polymer sample is rho sub S. Okay. Then, since both crystalline and amorphous regions basically form the total sample, total volume of the polymer sample will be crystalline region, the volume of crystalline region plus volume of amorphous region, right? Also, the weight of the total sample, so this is, okay, will be sum of crystalline and amorphous region, right? Okay, and since weight is density times volume, right, which can be, this equation can be written as rho S in this way, right? And since VA is in this equation, we can use the first equation. We can say that rho C VC plus rho A Vs minus Vc, right? Okay, so if you rearrange it, okay, what you can get is that rho SVS minus rho AVS is equal to CVC minus rho AVC. So as a result, what you can get is that VC over Vs, the volume fraction of crystalline region, is rho S minus rho A minus over rho C minus rho A. Okay, this is the basically volume fraction of crystalline region. Okay, so as a result, degree of crystallinity, Xc, which should be the weight ratio of the crystalline region and overall sample, which is this. Okay, and we have Vc over Vs here. Okay, so if you put this in here, what you get is that rho C rho S times, okay, so if you know the information about the density of the sample, density of the crystalline material, the crystalline region, density of the amorphous region, then you can determine the degree of crystallinity. Okay. Okay. Another method to determine the degree of crystallinity is based on X-ray technique by simply checking the crystal structure. So which is, the technique is called wide angle X-ray scattering or wax. Okay. So simply by using the X-ray technique, you can determine the crystal structure. Okay. So if the sample is totally crystalline, okay, what you will get is this kind of peak, right? Sharp peak. If it's not crystalline, if it's amorphous, you'll basically get some background signal, right? In real sample, you'll get both, right? Something like this, right? So by simply checking the ratio of the area, crystalline region, basically this region, and amorphous region, okay, you can determine the degree of crystallinity, right? Okay. Another more common method is basically using the thermal analysis or using the DSC, differential scanning colorimetry. I believe that you guys have done it in a basic experiment, right? So if you measure DSC as a function of temperature, you can determine the enthalpy change. If this is XO, then you basically get this kind of graph, right? So here denoted as TG, okay, TC or TM, something like that, right? So you can determine the crystallization temperature, right?